official inauguration. This official inauguration of the Data Intelligence Institute of Paris. So let me say that diiP started operations last fall, but then we decided to have this official inauguration now. We were back then hoping that things will be also better with COVID, but in any case, I'm very glad that we all managed to be here together. So let me just introduce our first speakers. I'm very glad that we have with us the president of Université de Paris, Christine Clerici, and also the vice president for research, Edouard Kaminski, who will open this event. So if I may invite Christine Clerici to give us a welcome message.
Thank you, Temis, and good afternoon, everyone. Dear colleagues, it's a great pleasure for me to launch this first symposium organized by the Interdisciplinary Program on Data Intelligence funded by Université de Paris 1 year ago now. And just a few words about Université de Paris, which was created in 2020 by the full merger of two leading Parisian universities and the integration of IPGP. And each of these institutions had a long history of collaboration in education and research, and this merger was somewhat natural. As soon as it has been created, Université de Paris has been ranked among the best universities in the world and compete with the high-profile university in many disciplines, such as mathematics, IT, and life science and health. Université de Paris is a comprehensive university with more than 150 research laboratories, 10,000 of researchers and research teachers, and 3,000 PhD students, divided between 3 faculties: health, sciences, and social sciences and humanities. Health faculties is the first health faculty in France and in Europe, and offer high-level training and cutting-edge research in medicine, pharmacy, and odontology. The Faculty of Sciences included mathematics, IT, physics, chemistry, and biology, and the Faculty of Social Sciences and Humanities included a broad spectrum of disciplines from psychology, social sciences, linguistics, history of languages, and civilization. In addition to the quality of each of these 3 faculties, laboratories, and institutes, the Université de Paris is a unique, powerful, and innovative institution within French higher education and research, which is also very connected to a large network of universities in Paris, but also at the national level, and leading research organization in France, Europe, and the world. Because the university is a major place of education and research, and because of its social responsibility, Université de Paris is committed to working on the major challenges facing our societies: the climate challenge, social cohesion, and health and artificial intelligence, of course. We think that the solution and the progress will come from intensive research universities like ours, and the students trained here will be in the front line to invent, lead, and transform our future. To face these challenges, we have launched 6 interdisciplinary institutes, and the Data Intelligence Institute in one of them. These laboratories foster and support emergence of different disciplinary practices to meet these challenges by bringing together scientists, researchers from science, health, and social sciences. give the floor to Edouard, but I wish you an excellent meeting, and I guess that it will be the occasion to initiate a lot of interesting projects. Thank you very much.
Thank you very much, Christine, for presenting the university and also for your good words. Could I ask, please, Edouard Kaminski, Vice President for Research, to give a welcome message?
Yeah, for sure. Hi, everybody. So it's a pleasure to be here today, and I will just add a few words on the first presentation by our president. So I will say that Université de Paris is built on a faculty model that highlights the strength of our disciplines in science, health, social sciences, and humanities. But our university wants to project itself beyond the disciplinary fields and has decided to put interdisciplinarity and the dialogue between disciplines at the center of its political and scientific ambition. So to that end, we have identified key issues for society today and society of tomorrow. And we have decided, thanks to the financial support of our Initiative d'Excellence, IDEX project, to fund actually 9 interdisciplinary institutes to deal with these societal challenges. So I won't give the list of these institutes. You can find them on the internet, but I would say that they range, for example, from global studies, of policy and climate changes, to the person beyond the patient in medicine, from a space hub to the study of the origin and societal impact of the COVID crisis. So these are very wide topics and very complex ones, and we are sure that interdisciplinary is the key to solve them. These institutes have a strong research dimension, of course, but we also expect them to carry on educational projects and to be also laboratories for new technological transfer in these important questions. As such, I guess that the Data Institute of Paris is a perfect example of the ambition of Université de Paris. And I'm very happy to see that many people are connected today to discover more about this institute. So it is really a pleasure to see this first kickoff meeting of the institute, and I'm sure that future will be great for all the colleagues involved. So thank you again for this work, Temis, and thank you for this great departure. Thank you.
Thanks for the nice words, Edouard. So now let me spend a few minutes to say a few words about what this institute is about, and also let you see what the rest of the agenda for today is. So I will share my screen. Okay. So this is just a reminder of the agenda. So I will just spend a few minutes now presenting diiP, and then please remember that after that we will have a presentation of the master's projects and the strategic projects, and in between we have 2 invited seminars by Donald Kosman. He's the director of Microsoft Research in USA, and by Ian Foster. He's the director of Data Science and Learning Division of the Argonne National Lab from the United States as well. So let me just say a few introductory words about diiP. So first of all, as mentioned earlier, diiP is a Université de Paris IDEX interdisciplinary institute, and the main goal is to promote interdisciplinary research on data-intensive problems. I will come back to exactly this point. I would like to thank all the people that have spent lots of time and effort in trying to make this happen. and this includes mainly the people at the executive board, which are listed here. And as you can see, they span from several different disciplines, including all 4 partner institutes of diiP, which are the Université de Paris, Sciences Po, Université Sorbonne Paris Nord, and INED, it's the National Research Institute for Demographics. Of course, nothing of this would have been possible without the help of Anaïs Demuret. She's our project manager. So the disciplines that are involved in diiP cover pretty much the entire span of our university, and this involves some foundational sciences like computer science, mathematics, statistics, physics, chemistry. These are sciences that provide tools to analyze data and build models for different phenomena. And of course, life sciences, material sciences, earth sciences, sciences of the universe, and social sciences. So really a very vast spectrum of disciplines ranging from biology and seismology all the way to social networks and demographics. And all these are sciences that that come with very interesting and challenging problems. Several of them are key problems in our era. And they also come with lots of data that they need to analyze in order to produce some results, discover patterns, extract new knowledge. So the reason why we thought that diiP will be a nice initiative is that we nowadays can observe different real-world phenomena at a level of granularity that was never before possible. And this leads to the production of data sets that are both very complex, so high dimensionality, heterogeneous data, as well as large scale, so up to terabytes for even a single experiment. And all this data, they need to be analyzed because this is for a large part nowadays how we can make scientific discoveries by looking at the detailed fine granularity data measurements that we're doing. This allows us to refine existing or build new models that explain how our world and the universe operate. And but of course, this analysis becomes extremely challenging because of the size and the complexity of the data. And this is why we need new analysis and intelligence techniques that will be suitable for to this purpose. And one last point here is that in several cases, the domain experts may not be also data analysis experts. And may not be able to analyze the data that they already have in their full detail or to their full potential. So what diiP wants to do is to get all these researchers that are working on data-intensive disciplines, disciplines that by nature produce lots of data, bring them together with researchers that work on foundational techniques and methods and algorithms that allows us that allow us to analyze data, extract new knowledge. So we want to bring together world-class experts conducting cutting-edge research in these two directions, and these are experts that are part of diiP. They are part of the institutes that form diiP. And the mission of diiP is to identify fundamental methodological questions across different research fields and disciplines, establish long-lasting interdisciplinary collaborations, and by this enable breakthrough results based on data analysis, enable breakthrough scientific discoveries. So in this process, we hope that we will build tools that individuals and as a community we will be able to reuse for different problems, different projects, different disciplines, as well as build a community around this area. Last but not least, we hope that in this journey, we will also manage to educate a new generation of researchers. So undergrad students, master's, PhD students, knowledgeable about data science and data intelligence, informed about and open to work with other disciplines. And this is something that cannot be taken for granted. Interdisciplinary work is challenging. And of course, we hope that this new generation of researchers will be better adapted to the market needs, which now ask for research and technical skills in this area, data intelligence and interdisciplinary projects. So the way that we're trying to accomplish these goals is through research seminars and workshops. So this is by having seminars by internal or external guests on different scientific problems, as well as hands-on mini tutorials on different tools and methodologies. We are planning to have these seminars and workshops in late afternoon, the first Wednesday of every month. And we will soon send out an announcement with the upcoming seminars and workshops that we are planning. At this part, I would like to mention Ms. Fula Vagena, who is one of our two research associates, who has already done quite a bit of preparatory work for building some hands-on tutorials on different aspects of data intelligence. So you will certainly be hearing more from here in the coming months. And the second direction that diiP is working on is on supporting collaborative projects. Collaborative means between different disciplines to the extent possible. And this is done through the master's projects. So diiP is funds master's internships on this kind of projects through the strategic projects. And this is unfortunately a smaller number of projects due to budget constraints. Projects on interdisciplinary problems. And these are projects on which the two research associates of diiP have already started working on. And finally, we will have PhD scholarships, and these will be scholarships on topics related to data-intensive artificial intelligence. And this will be announced soon. So up to now, what has happened is that we really started operations in September 2020. So this was just a few months ago. But despite that, we tried to move quickly. So we had our first call for proposals in October. we received many proposals covering many disciplines from all faculties. And out of those, we selected and are currently running 16 projects for 2021. And as you can see in this pie chart, these projects involve all these different disciplines from the diiP partner institutes. So I'm extremely happy that we had such a diverse set of researchers interested in what diiP wants to promote, and I'm also happy that we can reach out and help in one way or another to all these different disciplines. As I mentioned, there will soon be announced support for 12 PhD scholarships. This is co-funded by the ANR based on the data intensive artificial intelligence project that we submitted, I think 2 years ago. In summary, the Data Intelligence Institute of Paris wants to identify data analytics needs and requirements across different disciplines, support interdisciplinary actions, projects, collaborations, and build and reuse generic data analysis pipelines. We will develop our actions along all three axes of research, training, and documentation, and in the process promote open science. So this is once again the agenda for what follows, and I guess this is what I wanted to say. One more thing, if you have any questions during the event, please post them in the chat. We will be following the chat and allow questions in the meantime. So I guess the next item now in our list is the presentation of the master's projects. We have selected and currently running 13 such projects, which are projects that involve, as I said, a master's intern that is supported by diiP. One last comment. I have to say that we're always trying to support a variety of interdisciplinary projects. So I would like to ask you once again to submit your projects for next year. So the next call will once again run sometime in the fall. So September, October, we will announce everything before that. But just be prepared and rest assured that we're here to try and support this kind of projects. So if there are no comments on all this, we could now start the presentation of the master's projects, and this will give you an idea of the different scientific problems and challenges that we will be supporting this year.
Thanks, Temis. So the first one to go is Agata Trovato. Are you ready?
Yes.
Okay.
Should I share my screen or you have the slide?
No, I will share my screen actually because I will run all your presentations. so we don't have to share a screen to change the screen every time.
So while you look for it, I can introduce myself. So I'm Agata Trovato. I'm a researcher at APC in Paris. And so the project that we are working on is called Malvasia. Is an application of machine learning to the analysis of gravitational waves. So according to general relativity, we know that when in cases when, for example, a small compact object very massive in our universe, like black holes or neutron stars, are spiraling one around each other, they reduce the radius of their orbit and arrive to the phase of Ranger, and then there is a ring down, and during this phase, gravitational waves are produced. You see in the left part of the slide what are the prescription of general relativity. We expect this wave that has frequency and intensity increasing while the two bodies get closer. The detectors are interferometer, of which you see some pictures in the left part of the slide. And usually they work in coincidence, because the problem is that this signal, this gravitational wave signal, very faint, and we have to find them in a background that is noisy and is polluted by short-term artifacts that are called glitch. And this can mimic the gravitational wave signal. So looking for coincidence between multiple detectors allow us to distinguish what is the signal that will appear only in one detector, so in multiple detector, with respect to the glitch that will appear only in one detector, because they are a detector artifact. So in the case when only one detector is taking data, this distinction is much more complex, and what we are trying to do is develop a convolutional neural network that is able to classify our data in 3 classes that I've summarized in the right part of the slide. So noise, so almost Gaussian noise, the typical data that comes from the detector where nothing happens, basically. Then the signal, so the gravitational wave signal injected in the noise, and you see this is the blue black time series where the signal is in red. And then the third class is the glitch, and you see here I took just as an example of glitch, but the glitch are they vary a lot in shape, morphology. This is just one random example. So we are doing this with convolutional neural network. We already found a student to continue the project, and you see the list of collaborators that is a mixture of expert of gravitational waves and computer science expert. That's it.
Thanks, Agata. So the next one in line is Charles Lelaske. I don't know if he's ready.
Yes, I'm there.
Okay, thank you. So, yeah.
So I'm Charles Lelaske. I work at the Institute of the Globe Physics of Paris as an assistant professor. I'm working on the properties of lavas and magmas and their link to the dynamic of volcanic eruptions. As you can see, for instance, on the figure on the left, I simplified a plot, if I can say, that we see lava flows, fountains at the top left, and we have also different, even a volcanic plume on the upper right. We know that all those types of volcanic eruptions are governed by 2 parameters, the mass discharge rate and the viscosity, and other parameters, of course, but those 2 parameters have a strong influence on the volcanic eruptions. And I'm trying particularly to know more about how viscosity of the lava changes with its chemical composition and other parameters. We are doing that because we don't have a general model to predict it. So we tried using an artificial neural network. You can see a schematic schematic drawing there on the right, where we impute the lava composition, and we can have prediction of different properties, including this viscosity. It works very well. You can see on the bottom right that we have a very good prediction in orange compared to what exists, which are the dark, it's another model, which are the dark symbols. But for simple systems, so the goal of my project, which will be led by Barbara Baldoni, which is a master student in geophysics, will be to include new elements to make the model more and more pertinent for natural compositions. We will try to see if we can use transfer learning, or we need to start the training from scratch. And I think it's a good opportunity for Barbara and I to learn new things about both machine learning and earth science, and develop this model to apply it for volcanic eruption in the future. Thanks for your attention.
Thank you very much, Charles. And the next one to go is Florence Club.
Yes, can you hear me?
Yes, we can hear you.
Yeah.
Thank you.
Thank you. So I have just 2 slides. So just for the first slide, so I'm from Clope. I'm from the LIPAD and an associate professor. And I'm going to work on combining visual and textual information for enhancing image retrieval systems, and usually for radiological practices. So it will be done, we have already recruited the master student intern, and it is the project will be done in collaboration with Laure Fournier, Dr. Laure Fournier of the Hôpital Européen Georges Pompidou. Can you move to the next slides, please? Yeah, so the aim of the project is to query packs from, so it is a system that is designed for archival purposes, for to store the images that are taken in the hospital, for example. But the main problem is it is not designed for retrieval purposes. So we can only search by keywords regarding the patient name, the date of the examination, and the type of the examination, which is not very user-friendly. And we want to have the functionality of being able to query the packs with the images. And the solution we are going to investigate is that we are going to integrate higher level images, image descriptors, and semantic terms that can be extracted from a text report, radiological reports, for example. And we are going to use deep learning approaches that gives promising results in radiological report mining, and also for visual search image. And the main idea also is that we want to query not only with one image, but with a sequence of images, for example, and combine these sources of images with a text report. So that's all. I don't know if you have any question.
Thank you very much, Florence. I think we can save all the questions for the end.
Okay.
And the next one in line is Frédéric Austerlitz. Don't know if he's here. Frédéric. I think I saw him in the participants list earlier. Okay, so maybe
typing in the chat, if I may.
Thank you. I didn't see.
We can hear you. Oh no.
No, we cannot. Yeah, it is Frédéric. We cannot hear you, Frédéric. On vous entend pas.
So maybe we can go to the next one, and Frédéric can resolve the problem.
Yes, Of course. So the next one is Antoine Prosper.
Yep. Hi.
Okay. Hi. So this is a slide, right?
Right.
Okay. Thank you.
So, hi everyone. My name is Antoine, and I'm a Master 2 student from the Biomedical Engineering program of the Université de Paris. I started my internship at the Centre Borelli, which is essentially a laboratory embodying the partnership between Université de Paris and the ENS Paris-Saclay, where the teams try to integrate fundamental and applied mathematics to life sciences. And in the case of the team I joined, they're trying to integrate those tools to neuroscience to try to model brain activity and quantify human behavior. So the leader of the team is Laurent Houdre, who's a professor at ENS Paris-Saclay and a researcher in signal processing, pattern recognition, and machine learning. And working with him is Pierre Humbert, who defended his thesis last month on mathematical tools for large-scale data analysis, and Clément Dubost, who's the head of the anesthesiology department of the Hôpital Bégin in Saint-Mandé. The project of the team is to implement machine learning tools for the study of EEG data that was recorded in humans under general anesthesia. And the motivation behind the study is that although medically speaking, the effects of general anesthesia are considered to be fully dissipated 3 hours after the patient has woken up from surgery, some key indicators of general anesthesia, which you can see in the middle of the slide as oscillations between 8 and 12 hertz, which is called the alpha oscillations. Well, those oscillations are still visible in some patients, even well after the 3 hours mark has passed. So our goal is to investigate and actually give quantitative information about those observations and to potentially uncover any cognitive repercussions in the patients that still show these oscillations even after the 3 hours mark. Thank you.
Thank you very much, Antoine. So is Laurent, Frédéric's issue solved or not? Doesn't seem like that. Okay, so the next one in line is Marc Huertas company. Maybe he's here.
Hi, I will speak on behalf of Marc, who could not join today.
Okay, thank you.
So I'm Alexandre Boucaud. I'm a research engineer working at APC Paris. So I'm working on in collaboration with Marc on a subject. So it's an astrophysical subject. We're looking at, so if you look at the bottom image, this is an image of galaxies. So it's a crowded field of galaxies that will be seen by the next generation astrophysical surveys. Because we can see much more light than before, we're seeing many galaxies. And so in most of the cases, so more than 50% of the galaxies will be what we call blended, which is what we can see on the image above, where actually the flux of the galaxies are overlapping. So because galaxies are made of void, basically, all the photons come through, and so we're always seeing one galaxy on top of the other. And that's a problem for general cosmology, to be able to, because what we want is to know exactly which photons are coming from each galaxy. So that's the problem we're attacking here, is to be able to disentangle which photons come from which galaxy and to separate them, which is what we call deblending. So the approach that we're going for is to use a deep neural net called the UNet that is able to, given an image of galaxies in several wavelengths bands, to be able to separate these galaxies. And more specifically, we're trying to use a probabilistic UNet, because what we want is to be able to look at the uncertainties of these neural nets to affect each pixels with a probability of belonging to one galaxy or the other. And so we're really grateful for that grant, because it will allow Thomas Sinra, who is doing a gap year currently in our group to move to Marc Huertas Company's group and foster that collaboration by working on another instrument and see how combining two instruments can really help.
Thank you very much, Alexandre. Next one in line is Marcela Sopos.
Yes. Hello, everybody.
Hello.
Thank you, Anaïs. I'm very happy to be here today and share with you this presentation of our project, which is at the interface between mathematics, computer science, engineering, and medicine. And what we aim to do is to understand the different risk factors in the progression of a condition called glaucoma, and also to assess the different factors that contribute to the efficacy of a specific medication, and all this on an individual specific basis. How do we plan to do that? It is to take as a starting point a clinically collected set of data, which is the Indianapolis glaucoma progression study. And thanks to that, we will be able to feed on an individual specific basis a computational framework that we have been developing for several years, which is called the Ocular Mathematical Virtual Simulator. And through this mechanism, we will produce a simulated data set that, together with a collected clinical data set, will lead to what we call an enhanced data set, which is richer than what we had at the beginning, because you have both access to measurable information, but also non-directly measurable information. And then we can analyze all this data in order to answer to the question that I mentioned before. So just to present the team, I'm a professor in applied mathematics at the University of Paris. And we will work with Professor Giovanna Guidovoni. She works in the University at Missouri, jointly in mathematics and engineering, and with Professor Aaron Harris, who is an ophthalmologist, working at Mount Sinai, New York. And previously he worked in Indianapolis, and this is where he was able to collect this rich set of data that I mentioned earlier. And so in this scientific venture, we were joined by Damien Cole, who is a second-year master student in Mathématiques Modélisation Apprentissage master training at the University of Paris. Thank you.
Thank you very much, Marcela. So last call for Frédéric Austerlitz. Maybe it's going to work. Yes, no. Okay, doesn't seem like that. So next one in line is Camille Kurtz. And I just need to move from the PDF to the PowerPoint.
Hello, good afternoon, everybody. Can you hear me?
Yes, we can hear you.
Okay, thank you, Anaïs. So in this project, we work on the analysis of satellite image time series for the mapping, for the automatic mapping of territories. And this is a collaborative project between researchers from computer sciences and geosciences, from the LIPAD for computer sciences and from the LIV for Université de Strasbourg, with Anne Puissant, who is a researcher in geosciences. And we'll work with Luca Colomins as a master student for this project. Can you please move to the next slide, Anaïs? So the aim of this project is to analyze the satellite image time series for the specific task of the mapping of the vineyard in order to update databases in a timely and accurate manner. And we focus here on two main problems. The first one is that classical deep learning architectures that are used in the literature to analyze satellite image time series only rely on temporal information. And from a thematic point of view, for the analysis of vineyard, these crops can have different visual appearances. For instance, given the color on the spatial arrangements of trees, And this will be useful to integrate also spatial information in this analysis. And also the second problem is the lack of training examples when we consider this specific task. So for vineyard mappings. And in this project, we investigate to consider novel two-dimensional representations that encode in one single representation both spatial and temporal information, and we'll also focus on a novel type of images called Venus images that have an improved spatial resolution. And this work is based on a previous work where we focus on the analysis of sentinel images that are image time series with a lower spatial resolution, and here we want to adapt the architecture of an existing model in order to modify the features that can be learned to detect the vineyards from the images. And has expected results and an impact from a data science point of view. The analysis of two-dimensional data can have several advantages because we can include in one representation time and space information that can ultimately improve the results for this novel application. And from a geographical point of view, many vineyards are actually not recorded in the RPG. This is the national database of crops. And such a database is used as a reference for monetary assistance by the Common Agricultural Policy in Europe. And there is a need of a real-time agricultural monitoring system. So that's all, and thank you for your attention.
Okay, thank you very much, Camille. So the next PowerPoint is about Nicolas Ballier's project, but he has recorded an audio already, so I'm just gonna play the audio.
Projects called complex theories. It investigates the misfires in neural machine translation, looking at both the complexity of the inputs and the visual interpretation of neural network. As can be seen on the screen capture, when translating a sentence like "the nurse has finished his job," find that his actually shows attention.
We don't really hear the
words.
Yeah, I just saw your messages. If I
No, Anais, you have to, before starting the screen, you can click on sharing your computer sound.
How do I do that? So I need to click on new sharing, nouveau partage.
Maybe you unshare, and then when you start sharing on the bottom, bottom left, you see something where you can say share computer sound.
Yes, I got it.
Okay.
Hold on, I need to just put my password. Okay, so actually it doesn't work. I'm sorry, my whole computer was off for a minute.
Anais, I can just do it very quickly then. And you can
oh, you're here.
Yeah, sorry.
Okay.
So we're working on neural machine translations, translation that's done by a neural network. And even though it's done tremendous progress, we want to solve some issues such as mistranslations for gender, for example. The nurse has finished his job will be translated as l'infirmière a fini son travail and not l'infirmier a terminé son travail. So we want to achieve a better understanding of what gets wrong of the misfires in neural machine translation. And our idea is to try to associate two tools. One is the analysis of complexity. What happens if there are many, many words between the antecedent and the pronoun? What happens if it's a more complex sentence for the analysis of it? And the second technology is neural net visualization. So what you can see here is self-attention, but we can also do cross-attention. And we're trying to understand how the neural network will pick up the next word which is used for the translation. So you can see a whole series of heads and the corresponding line, and we want to see and understand why his does not refer to nurse. And that's the idea of visualizing attention configuration, attention matrices. We expect to try to see a correlation between our measurements of complexity and those attention matrices, and possibly to try to find out some thresholds in complexity that would result in certain configuration, looking at both the different heads and the various layers of neural networks, as can be seen here with the 7th layer in the illustration. We hope to end up with better training data to get better results. And this is a truly interdisciplinary project with colleagues from the Computational Science Department, Jean-Baptiste Younes, colleagues from the Linguistics Department in Computational Linguistics, and our intern is Na Wang Dipenda, a student from the École d'Ingénieurs de Denis Diderot. Thanks.
Great, thank you very much, Nicolas. Next one in line, and actually previous one because I forgot you, Laurent Venling. I'm sorry if you're here.
Okay. Hi, everybody. So this internship project can be considered as a basis of new collaboration between l'IPAD with Camille Kurtz and Nicole Vincent, and also Gaël Dufour from LISA. So the aim is to provide spatial and temporal descriptions of the various pollutants from the urban scale to the continental and global scale based on satellite observations. That's about 1 million of measurements per day represented as images. So we can see a sample at the bottom right. And there are two main challenges. On the one hand, it involves analyzing of this data in an objective way to identify pollution events, track pollution plumes, and their evolution over time, and also identify the anthropogenic and natural origin of these plumes. On the other hand, it involves designing algorithms which are dedicated to the analysis of satellite image time series through image analysis and AI paradigm, and to be able to deal efficiently with missing or incomplete image data. So here the goal, in fact, is to identify the plumes from naive regions of interest. And we will consider 3 main steps. The first step is to manage the missing uncertain data to restore the plumes, for example, by evaluating spatial positioning on seed regions. We will also study the tracking and visualization of the plumes over time. And then the study of the interest of adding other data to build plumes could be performed, but it's more, in fact, exploratory. Finally, the expected result is the automation of an atmospheric data processing chain to process huge volumes of data. And to make this, we have recruited one master, which is with Camille Arguello. So thanks for your attention.
Great, thank you very much, Laurent. Next, we have Sylvain Laubry.
Yes.
Yes, and there.
So everyone, indeed, my name is Sylvain Laubry. I'm at the conference at LIPAD, and I will present our master's project that tackles the automatic production of environmental indicators from freely available remote sensing data. So this is a joint project between Université de Paris and Institut National d'Études Démographiques. And the participants are Géraldine Duté and Valérie Golas from INED, and Camille Kurz, Laurent Van Ling, and I from Université de Paris. The student working on that will be Salma Dahdouche, a student from INSAT in Tunisia. So the context of this project is the following. The study of the population is generally made at a local scale with frequently updated data, or at a global scale through censuses which are much less frequently updated. And in this project, we want to study the feasibility of producing and using environmental indicators for demographic studies. To this end, we'll propose a deep learning-based method for the classification of local climate zone, which is the nomenclature used in a variety of thematics. And this extraction will be made from Sentinel-2 images, which are produced by the European Space Agency. And we'll have the problematics that it should work for less developed areas. And this last constraint is not straightforward, as methods for this kind of problems are generally trained and evaluated in well-developed areas. So we propose to use spatio-temporal constraint in a deep learning methodology, and we'll study our method in Ouagadougou and Antananarivo, sorry for the pronunciation. And a final step of the project will be to start a reflection on the impact these indicators will have for the population. And as such, this project will have an impact on the study of population, obviously, but could also be useful in other domains using local climate zones in developing areas. Thank you.
Great. Thank you very much, Sylvain. Then we have Zoe Kapula.
Yes.
Yes. Okay. Thank you.
Thank you. This is a triple cooperation. We start with the laboratory IRIS, CNRS, and the LIPAD, and also a small company that comes out from the laboratory, which is called Orasis. Next, please. Our expertise is the eye movements, the neurology of eye movements, which are very important for understanding how the brain functions. It's actually a biomarker that can give us lots of information about brain function and lots of neurological diseases, but also about children and school learning difficulties, namely dyslexia, that concerns many, many children all over the world. Next. We have produced on the basis of our research a device that allows us to test and eradicate the abnormalities of eye movements. And we use software which is until now based on threshold and velocity. And our goal is to go further in implementing new approaches based on artificial intelligence. Next, please. We have shown that on the basis of the trajectories of eye movements, you can see abnormalities in the dyslexic children relative to non-dyslexics, and abnormal eye movement traces during reading. Next. And the project we have now with the diiP is to go further in prevention and to make a screening study in the maternal school very early before starting the real school to detect these problems as soon as possible. By implementing an artificial intelligence approach, we hope to identify the patterns that are specific in a very early stage so that we prevent the problems. And for this, we hired a student who who will work together with me, Joanna, and also with the PhD student who is also sharing artificial intelligence expertise under the guidance of Temis and myself. Thank you very much.
Thank you. So if we don't have Frédéric Austerlitz back, maybe we do.
Do you hear me?
Ah, on commence à vous entendre, mais...
Vous entendez là?
C'est un peu compliqué là, c'est pas très net.
Okay, so may I suggest that Frederick, you may send us your presentation recorded, and we can add it. If we can share it if you want.
Okay. You still don't hear me now?
Now, yes.
Okay.
Do you hear me now?
Yes.
So I can start the presentation now?
Okay.
Ah. So it is this one, right?
Yes. I will do it quickly. You still hear me?
Yes, thank you.
Okay. So the subject of our project is inferring cultural transmission of reproductive success through machine learning methods. So we have already hired an intern named Ferdinand Petit from the Master M2 Bioinformatics from the Université de Paris. So the problem is that you have a process called cultural transmission of reproductive success, so CTRS, which occurs in several human populations, and it sees when a sociological process, when people from large families, their children have also, themselves, they will have also a lot of children. So positive correlation between the number of children from an individual and its descendants. So method has been developed to detect this process from small DNA sequences. And the question we ask is, how can we adapt them for large recombining next generation sequences, so like whole genome sequences, to improve inference? So our proposed solution is to adapt an existing program, SLIM, to perform extensive simulation on the impact of cultural transmission of reproductive success on next generation polymorphism. And we will use this simulated data as a training set to infer this process on real data, and so with machine learning. So we will do it either first by computing summary statistics. This method is called approximate Bayesian computation, or we can also do it directly on the data. So we expect several results and impacts. So we expect to develop an effective simulation program, and then a computationally intensive method that will be then validated and applied to the real data. So this is a quite interdisciplinary project that includes both biology, computer science, and also social sciences, and demography to some extent. And so it will be run by myself, so I'm senior research director, with the help of one of my PhD students, Jeremy Gave. And this will be in collaboration with Florence, with an informatician, a bioinformatician localized in Paris-Saclay, and who is specialized in machine learning. So that's it. I thank you for your attention, and sorry for all the problems.
Thank you very much. So Temis, I give you back the floor. Then.
So thanks to all the people involved in the master's projects for these presentations. So I hope that this is also an opportunity to incite new collaborations or ideas. Let me immediately pass to our next point in the agenda, and this is an invited short presentation by Donald Kosman. I'm really glad that Donald was able to find some time and be with us today. Donald is the director of the Microsoft Research Lab in Redmond, in the United States. Before that, he spent many years as a professor in the computer science department at ETH Zurich, He's an ACM fellow. He has been chair of ACM Sigmund, and he's one of the very well-known researchers in his field, data management and cloud computing. So, Donald, the floor is yours.
Okay, thank you very much. I'm trying to share my screen. I don't know whether you can see this. Can you see the screen?
Now, yes.
Okay. Yeah, so I've just heard all the exciting projects, so thanks for having me. And I'm probably preaching to the choir here, so a lot of the things you said I'm going to just echo. But let me just take a step back from and give my bird's eye perspective on what is happening. I think in the last 6 talks, everybody was mentioning machine learning and AI in some form, in some scientific context. And I would like to kind of take back and explain a little bit why this is happening. And so the talk is essentially about why AI is relevant for everybody. And that is preaching to the choir because you're already exercising it. Everybody here in this auditorium seems to be doing that, but also for everything. And what I mean here is, of course, all the scientific applications that you have in mind, but many other more mundane applications, and I'm going to give examples for that. So let me, whoops, why isn't this working? Why can't I move forward? Okay, let me just try. So let me just step back and say, what is traditionally science or kind of what computing or computer science about? And it has been mostly about creating rules. So if you think about Newton, what he has done, he has created the laws, or call it rules, of gravity. And he put it in formulas. Einstein kind of got insights about the relativity theory, and they've produced formulas. And what we've been doing as computer scientists, or as in that business, is we've been formalizing them and implementing them and essentially automating them. And so what we are seeing in this AI revolution is that there is this other trend. One way is to formalize everything into rules. And then there's this new trend where you just take huge amounts of data or experiences, the observational experiences that a scientist like Newton or even Einstein had to create rules, but you just leave it as these experimental results. You add a lot of compute to it, and then you essentially are able to answer or make predictions in the form that you have shown. And of course, this was most importantly for things where we couldn't find rules. Yeah. So for example, natural language processing, it was really hard to find all the rules that would define the French language, because there's so much more to the French language, so much more context, so much more culture to that language, that you cannot just put that all in rules, or the rules would be just as big as the data set of experiences. So if you kind of go to the mathematical foundations of this, rules, the mathematical foundations are logic. You have logic that say, well, if we're on the planet Earth, our gravity constant is like that, and then we will apply this formula. Whereas the AI or machine learning that you've been all talking about is mostly about statistics. And where this has clearly won, is for all perceptual tasks like natural language processing, language understanding, self-driving cars, visual computer vision, and so on. I have here like an example with many companies who've been investing here and who have astonishing results, like just to mention our own Microsoft, the translation. Google has also done that, but you can do a Skype call and you can translate. My talk now could be easily just automatically translate in French on the fly. So what this is, what I'm going to talk about in this talk is that this way of thinking is also very, very relevant for mundane tasks, for the more traditional computer science tasks, and I will explain why. And it's actually very beneficial, and I'm going to give 2 examples for that. The other aspect of, and so here's just a primer, but again, preaching to the choir here. You've looked, these are all examples where we all think that logic is probably not the right way to solve it. And just recently, both Microsoft and Google actually had some huge results on protein folding, where there was no kind of logic. It was really the magic of big data and big computing. So let me go to the other aspect very quickly. Again, you will all understand that because you're in this business and you're not really affected. But actually, I do believe that there's going to be a major shift here, that just really literally everybody needs to be empowered and needs to benefit from AI. And so those are the key ingredients that you need. So I talked already about data and about computational power. And not everybody has that available. And of course, you're privileged, as I saw, you have data, you have satellite images, and you have data that you can collect because special medical devices. And so you have that. You also are privileged because you have quite an amount of computational power. But again, it's probably not as much as like the big tech companies, including Microsoft. And then there's a third component that you need, and that is talent. And historically, these three components, maybe the universities had them, but other than universities, really only the big tech companies had them. And I believe there's just, as a side note, there's going to be a lot of change here, or there's a lot of change coming, essentially because of cloud, which makes big computation, but also data available to everybody, and research in computer science, like the research done at Microsoft Research, but also at many universities in computer science, that will also make it possible to democratize AI and make it really available and accessible and overcome these barriers of massive data and computational power and special talent that you need to everybody. So let me just dive into two examples and then maybe take some questions as I'm plowing through here on how this is really impacting computer science as my discipline in a pretty fundamental way. So as a first example, I want to give sorting. I don't know how many of you are computer scientists, but as a computer scientist, this is when I studied computer science and I was in the first semester. I was taught bubble sort, a way to sort. If you have, let's say, a list of books and you want to sort them, and essentially what this algorithm does is it compares two books. And if one is kind of alphabetically, the author is after the other one, you swap them, right? And you do that iteratively many, many times. So you don't, if you're not a computer scientist, if you're a computer scientist, you know this algorithm. If you're not, just intuitively think, you repeatedly compare two books and you swap them if they're out of order. And what is the modern form of that? And that might be a little bit surprising to you, is what you essentially do is you take a book and you predict where it should be. Yeah, and that's kind of a much simpler algorithm. So think of it just if you, how you kind of order your bookshelf, you might probably actually do that because you're not running bubble sort, obviously, because our brains are not very good at it. But you take a book and you see an author, or this book is by Tolstoy, and you say, well, I'm going to put that very far right because T is fairly far right. It's at the end, and there are not many books with authors. I don't have many books with authors of a Y or an X, for example. And so you essentially predict the position. And that's the machine learning way to do sorting, right? And essentially, if you abstract from this, is we're seeing a big revolution in computer science where instead of finding things, and computer science a lot is about finding. I'm a database person, Themis is a database person. It's all about finding. What we do instead of finding through comparisons, you compute things. And you do this for sorting, you can do this just for looking a book. Again, you would compute the position. And essentially, if you look at this, again, the mathematics behind this are very, very simple of this computation. I just did this, I'm just showing here an example. Essentially, what you do is you compute the cumulative distribution function. And that's really just machine learning 101. You can have it in any library. You don't even need TensorFlow or PyTorch for that. You can just do that. And with that, essentially, this function already gives you the position, right? Because it shows you for every kind of book, how many books are before that book? That's exactly what this function does. And so this is, and it's really now a commodity to do it that way. That's why this algorithm works. So why is all this happening? So one thing is hardware trends. Because of these massive investments into this AI for perception, for computer vision, and for all the things that you've been doing with CNNs, deep neural networks, there are accelerators for that, and that make this very cheap. And in particular, the general purpose CPUs, like the Intel CPUs or AMD CPUs, they do a lot of things that are actually not relevant anymore. If you can get rid of this comparing, which is actually a fairly complex thing, because you need to do a lot of optimizations, predictions, and the way computers are architected, this is actually an expensive operation today, whereas a multiplication you can accelerate very well and you can make it very energy inefficient. So hardware trends have actually come to a crossover point here, that a multiplication is almost cheaper than an if-then-else statement because it requires getting data from main memory into the CPU cache. The other trend that favors this computation rather than finding paradigm is security. Maybe you've heard of Spectre or Meltdown attacks. They all come from these if-then-else statements and speculation, optimizations that need to happen to make these if-then-else statements, these finding work. And so they are creating security problems, and they're going to get worse before they're going to get better, because we don't really have good solutions for them, except throwing performance out of the window, which nobody wants. And then there's a third part, which I would like to explain in the second example. That is, it's actually better from an engineering perspective. And the example I would like to give is selling ice cream. And what you can see here, I hope, is like a graph. How much ice cream you're expected to sell, let's say at the Université de Paris, on a day, depending on the weather. So I assume today nobody's going to sell ice cream, and that's partly because of COVID, but also, let's say, because of the weather is bad. But in the summertime, and once everybody's back on campus, depending on how much sun there is and the temperature, you'll sell more or less ice cream. And this graph essentially shows you how much consumption, how much sales you would expect on a day, depending on the weather. And this is the program, the traditional program, let's call it that way, that you would use to automate this. So you would somehow get the weather forecast, and then depending on the weather forecast, you would first decide whether you stay home. If it's less than 15 degrees, it's probably not worthwhile. Nobody's going to buy ice cream, or very few people are going to buy ice cream. So it's not worthwhile to get out of bed and worry about it. But if it's greater than 30, you're going to order something. If it's otherwise, you'll order, let's say, 10 liters or 25 liters, and then you're going to get up and sell the ice cream. And that's the traditional program. And I'm just going to show you what kind of the new style of programming, if this works, looks like. I hope you can see this. And this new style is essentially you're going to predict, obviously, the weather. You have to do that in some form anyway. But then you're also going to predict the consumption based on the weather. And this is going to be a task done by a data scientist, which is a very different function than the person. So everything that is here in orange is done by a different function than what is done in white, which is like the business process. And there's a data scientist that does the ice cream, the prediction of consumption, and then there's the normal business process developer that does the white part and says, well, if the consumption is less than 5 liters, I'm going to stay home. Otherwise, I'm going to order as much ice cream as is predicted to be consumed, and I'm going to sell it. And then again, I'm going to pass my experiences to the data scientists, and they should kind of retrain their prediction models. And what I would like to argue very quickly is that this second program is much, much better in many different ways than the first program. And that I believe that that's where we are going to go in terms of software engineering. And so the first observation is that the second program actually does separate these concerns. And that's actually very important. For example, if you have a new ice cream flavor or suddenly ice cream gets dramatically into fashion and your consumption changes a lot, then actually you need to change the program on the traditional software program, and you need to change, it might be constants, but you actually will end up having more if then else statements and be much more fine-grained. Whereas in the software 2.0 program, you will delegate that to the data scientist, and the data scientist will retrain the model, and it will be factored out, and you don't have to change any of the business logic. It's not intertwined. The other maybe interesting thing is if you look at the condition for the staying home, in the software 1.0, you kind of take a shortcut. You're not staying home because it's too cold for you. You're staying home because it's not worthwhile from the business perspective. And so if you look at the two conditions, they're actually different. And in the one, it is based on the temperature, which is not the right thing to do. And the other one, it is based on the business decision, it's not worthwhile. And so obviously that's what makes software so brittle, because you have many of these cutting corners. And then if something changes, like the fashion or your kind of your tolerance, what is worthwhile, you have to find all the places and you have to fix it. And that's how many bugs are created. I just have another kind of a brief example. You can extend this if you're worried about actually not the consumption, but ultimately you want to hard code the objective function. You want to actually predict what your profit is based on the temperature or based on the predicted consumption. You can have data science do that, and then you can even be more precise here. So I walked through this very quickly because we're also kind of to catch up a little bit on time. I'm going to skip the part that shows how this is going to impact the computation, and I really want to just go hand it back and then maybe answer a question. And with a summary that we are actually seeing, this is a much deeper shift than it looks like, where we're just saying we're going to do things differently. We're going to solve problems that weren't solvable before. We are now really going, in my opinion, to the next wave, where we're beginning to use these technologies, machine learning, data-driven technologies, to solve other tasks in a different way and probably better way based on hardware, software engineering and security trends, and that this is also going to be democratized for everybody and for all in particular also for small and medium-sized businesses. But what it also entails, and I hope I could give a little bit of a flavor, is that we're really reinventing the wheel here, beginning from just first semester computer science things like searching and sorting. And with that, thank you, and I'll take some questions if anybody wants to.
Thank you very much, Donald. So are there any questions after these very interesting observations that Donald has made? Maybe maybe till someone gathers up their thoughts, maybe I can ask two questions. So the first question is regarding these observations that you made specifically for software. So are these directions that you are now exploring in Microsoft for developing your different projects? So how does this affect the way that Microsoft now develops software?
Yes, so absolutely. So just to give an example, we have you're also a database system. I'm a database person. We have database systems that have like thousands of knobs, tuning parameters, right? And most of these tuning parameters are like if then else statement, right? If your main memory is greater than 500 megabytes, right? Then kind of your cost model is like that, or you favor a specific algorithm. If your workload is OLTP, you put the query optimizer on level 3, right? You have all sorts of these policies that you do for performance and whatsoever. And what we are beginning to see is that we want to kind of get rid of these hard-coded policies, rules, And we want to essentially put that into a model and try to estimate what is the best value for a knob given a certain situation. And we're experimenting with reinforcement learning for that, but it's not really important on that. So we are doing that also for a kind of our system software. We don't do as much of ice cream selling, but it translates these kind of policy decisions, which is also here. There's a policy, when to stay home, how much ice cream to order. You have that all over the place, in particular in system software. In the cloud, we're beginning to make important decisions where to place a virtual machine. If you come to the Azure cloud and you want to provision a new virtual machine, first of all, we estimate how long is it probably going to live, and then we have a model that tells you what is the best machine, because we want to defragment our clusters and so on. So yes, this is absolutely impacting us in a big way, and this is still at the beginning.
And just taking this, just zooming out from this question. So basically, we just discussed software development, but what about thinking about other discipline sciences? So traditionally, like in your example, we had people developing different kinds of models. Nowadays, even in my experience, I see more and more the young generations of students trying to answer to problems with deep learning. So I asked them, so how will you solve this problem? And their answer is, I will just run a deep learning algorithm. So where do you see the balance between these two worlds? And what do you see that the skills of the new generation of researchers should be to make sure that we get it right?
Yeah. So of course, if there's deep learning is one of these hammers where you think, oh, I'm going to put it into a deep learning network and then all problems solved, and I don't need to think about it, right? I'm not saying that rules should disappear, because rules, if you have a deep scientific understanding like Newton had or like Einstein had, this is always much more valuable than a black box deep learning model. And even if you have a little bit more advanced. So as scientists, we should still really worry about rules and understanding and deep insight, which you probably don't get very well from deep learning, because they are black boxes. That's one aspect. The other aspect is the cost. Deep learning is still very expensive. That's I skipped that part about the AI supercomputer. Modern machines are not built to efficiently do this. We are still 6 to 7 orders of magnitude worse than the human brain, than biology. I mean, we are much better with machines to do a multiplication, but we are much worse to do an inference or pattern matching. Our brain is just unbeatable in that. And so that's another aspect. So for scientists, I think rules are great, right? I mean, we want to create insights. For engineers, we want to solve a problem and there are many considerations like the performance and the energy efficiency, but there are also considerations concerning time to development. And then black boxes are sometimes good if they work, and that's why we use them for tuning parameters, because it's so complex, we just haven't found another way to do it. Yeah. So the balance, it depends, and that's what humans, engineers, scientists are still about, to strike this balance. I know that there's now a reflex to go to deep learning on everything, but it's not always the right solution.
Thank you very much for all these insights. Is there any last question for Donald?
Hi, yeah, can you hear me?
Yes.
Michael Ménager, I'm a group leader at Imagine Institute in Paris. I'm more like a cellular biologist, and to go along those last comments, I'm wondering if there are any studies where, to try to answer the same problem, both approaches are taken. One is relying on more classical, logical ways of thinking and traditional science, and then another one would be you ask the same question and then you try to solve it using some more machine learning based approach. So I'm wondering if such projects have been conducted, and if so, if we start getting results, and in how many cases using machine learning would be beneficial, and or what would be the negative and positive aspect of each approach, which would be more logics versus statistics. So I'm wondering if we start getting those type of feedbacks. Basically, take the same question and you try to use two different approach.
I think it's a great idea. And I think you at the university are perfectly set up to do these studies and answer these questions. I think it's a wonderful idea. Please go ahead. I'd love to get the results of these kinds of experiments and studies.
Yeah, because I guess that could help in the future to see in which cases we should invest, or for what type of question we should invest in more in machine learning, and for what other problems we could more rely on more logical rules. Right?
Yeah. Fantastic. Okay. Looking forward to your results.
Okay, thanks.
Okay, so thank you very much. Let's
last question.
Yes.
Yep. Donald, Yves Rosenthal, I'm a data scientist professor at the Faculty of Pharmacy. I'm just wondering, because your title was about democratizing, and because you have said that the price of learning, I'm not speaking of using, but I'm speaking about of learning, the price is so high for most of the researcher. How you imagine the future in order to increase the producibility and access to learning strategy for people who are not necessarily in very large university or even in private company like yours?
Yes, so I don't have a very good answer to that, but of course that's top of our mind. So currently what we are doing is we are trying to improve on our current procedures, let's call it computers, algorithms that we have, and we're trying to tune them as good as we can. And we're getting actually a lot of mileage of that. We're getting about a factor of 4 to 5 every year, if you just look at the sizes of models and that we're improving. But your question, I think, is really important. I think we have to do much more. And one of them is we really have to build new machines, which are actually completely designed for doing these kind of computations. And I actually believe that ultimately we have to get rid of this crazy algorithm, the statistical gradient descent algorithm, which is just incredibly expensive. And we need to reinvent other things. There are other things. For example, what makes brains so effective, biology so effective, is that we are able to forget. And computers are not able to forget, which makes them very inefficient. Forgetting is something really healthy, but it also helps us being efficient, because useless things we just forget. And computers never forget anything, and they carry around this whole baggage. So these are just some few ideas, but that's really research, as I put here, in the 2030 time frame.
Okay.
Okay. Thank you.
So thank you very much, Donald, for your presentation and the insights that you shared with us.
Yeah, thank you. Thank you. Thanks. Bye-bye. Thanks for having me. And enjoy your break. I know that I was running over for your break. Thanks. Bye-bye.
Thank you. Bye-bye. So we will now take a break for like 5 minutes, and we will resume at 5:15 with the presentation of the strategic projects. So this is just to grab a cup of water or something. So I'll see you in 5 minutes. And I guess we can resume now with the presentation of the strategic projects. So Anais,
yes.
Will you run the first two presentations, or shall I do this?
I can run the first two, yes, and then you run the one from Antoine Lucas.
Sorry, can you please repeat?
I said yes, I can run the first two, and
Okay,
then
okay.
you run the. Okay, so we can start with Michael Ménager. Then.
Okay.
Yes. Okay.
Can you hear me?
Yes, we can. I just opening your presentation on my computer and share my screen. You don't have any sound on your presentation, right?
No.
Okay, good. Well, there you go.
Okay, good afternoon, everybody. And so I'm very pleased to be here today to talk about our project Attraction and to talk about our already started collaboration with diiP. And so Attraction stands for Autoimmunity Inflammation through RNA-seq Analysis at single-cell level for Therapeutical Innovation. So this is a project led by Frédéric Rioloca, myself, Nadine Servan-Sasson, and Nicolas Garcelon. And this is a project which has been financed by ANR, and it's part of a RHU4 project. And you will, as you can see, we have a lot of partners that we're working with on this project: Sanofi, Arena Pharma, Hôpitaux de Paris, INRA, CEA, Pasteur, Curie, University of Paris, Sorbonne University, INSERM, and ANR. Next slide, please. So basically, at Imagine Institutes, we are interested in working with rare genetic diseases, so diseases that are characterized by identified mutation in genes. And so with some of my colleagues, we're specialized in studying disease of the immune system. And so for this project, there's a list on the left of 6 primary immunodeficiencies, so disease with autoimmune or autoinflammation sign. And so traditionally for those diseases, several genes have been identified. And so at the beginning, things were logical, which means one or several genes mutated for one disease. And the several genes mutated for one particular disease are part of the same signaling pathways. But then with the progress of next generation sequencing, we start identifying that different mutations in the same genes could lead to different clinical presentation and different disease. So which means now we can no longer rely on clinical sign combined with identification of a gene to try to understand the molecular mechanism and the treatment. And so we think this is part of what we call molecular heterogeneity, and this can lead to diagnosis and treatment wandering. So one idea when we started this project was to take advantage of the new technologies. And so since 2015, and it's now been possible to analyze expression of genes at the single cell level. So to isolate cells, in our case from the blood, healthy blood donors of patients with a known mutation, and then get expression of the top 15 or 20% of the genes expressed cell per cell. And so the way we've been using those data so far is we've been using those data to cluster cells based on their gene expression profile on those UMAP plot. And so our idea is maybe by comparing the profile of single cell clustering between healthy blood donors and patients, we could identify a cluster of cells that would segregate apart in patients. And if so, that would help us to isolate a molecular signatures from those cells and potentially biomarkers. Next animation, please. And so you can do that between healthy blood donors and patients, but you can also try or compare the single cell profiles with patients with the same syndromes, here AGS, and mutations in different genes. Maybe they have the same clinical signs, but their molecular profile could be different. And on the next animation, we could also compare with patients with different clinical signs, here SAVI versus AGS, where you might be surprised at the molecular level, they might be identical. And then we're also thinking in the next, with the next animation to compare a single cell profile before treatment, look at the impact of a treatment on this cluster of pathological cells and after treatment. And so on the next slide for this project, this is a very ambitious project. So we would like to not only look at gene expression profile of blood cells at the single cell levels, but we would also like to basically collect all those different omics. So the clinical phenotype, the genotypes, information of expression of the genes, expression of proteins, chromatin accessibility, which dictates gene expression, but also collect information from the lipids and the metabolites and the macrobiomes from the feces. And so here, this is where we identified that in order to try to use at best all those different multi-omics, this is where we feel like we need to try to use some semi or unsupervised approach by trying to use machine learning to try to handle at best all those big data. And so in the next slide, and so the idea here using machine learning would be able to potentially connect all those different omics together to try, for example, to predict if a patient has those specific microbes in the gut, that would imply that those potential genes would be deregulated. So this is here, you can stay on this slide, this is fine. Here, this is a description of a project. So the full project would be to analyze 200 pediatric patients and compared with a cohort of 250 pediatric patients compared to a cohort of 250 pediatric controls. Generate all those different omics, most of them at the single cell level, but not only. First, propose a new stratification of patients, not only based on genes identified and clinical phenotype, but based on those different multi-omics. And then trying to try to infer a network where all those different multi-omics would be all combined together. And the idea would be, once you've generated such network, you would ask, okay, if I see profile A, for example, to which subgroups this patient is more likely to belong and which treatment could be adapted. So one goal of a project is to try to get into more personalized medicine and personalized treatments and drugs repurposing. And so for this project, we are really glad to collaborate with Fula. And so we've already done a couple of meetings to try to see what needs to be done at the level of multi-omics data integration using some machine learning approach. So what we'd like to accomplish is first to identify the different methods existing out there for multi-omics data integration. And then, as we've talked before, we will try still to try to see there's some rules that could be established between the different omics, for example, transcriptomics, proteomics, lipidomics, or microbes, which could help somehow to try to have the different omics talking together. In the third step, to choose one or two or three different approaches, machine learning based, and start basically testing or data sets on those methods. And at the end, what's important is to start testing some models with our own data sets to try to see which one would be the most accurate approaches to perform the entire project. And so for that, we'd like to use to test our model based on what we call gold standards. So already known or published, linked in the literature between genes, lipids, microbes, or metabolomes, and see based on the data generated if we can retrieve those models. And so in the last slide, just to give you an examples, or in my team, where do we stand regarding multi-omics data integration? So this is a research we've published last year. We've been working with Richard Bono at the Simons Foundation in New York, and we've been using network inferences to try to connect genes together in this massive network. We connected 22,000 nodes, which are genes with more than 500,000 edges. And from that, once we got the network, we were able to identify some new transcription factors that would be involved in dendritic cells response to HIV or AIDS viruses. Thank you for your attention. And I think that's it. Thanks a lot.
Thank you very much, Michael. So the next.
So are there? So let's. So actually, in this session, we have up to 15 minutes for every project. So there is time for questions if there are any. Can I start with sure. With a question? So you mentioned the use of machine learning. So can you say a few more things about how exactly machine learning will help you. So what are the tasks that you could not solve otherwise, and you will be able to solve with machine learning?
Yeah,
and
also,
also,
yes,
and also comment on the issue of training.
Yeah.
So for machine learning, we also need training. So in your case, where will this training data come from?
Yeah. So I think what's interesting here is, you know, with each of those data sets, we could use what we've been defined today as logics. So we could take some data and start from what's published, and from what's published, try to look at what's out there from the data. And so we could try to jump from point A to point B, and then from point B to point C. But as you know, research is at the bench. You know, I'm talking at the, you know, for cellular biologists, takes a lot of time. And so here, the thinking is we would like to use some unsupervised approach with machine learning to, for example, predict that what's known is point A, but we should already jump to point Z because it's predicted to be connected to point A. So the idea would be there's nothing existing in the literature, but would allow you to think that to answer your question, you need to link A to Z. But since your machine learning approach would link directly A to Z, the idea is you use unsupervised approach to generate new hypotheses that are totally independent of what's out there in the literature. And then you get back to the bench and maybe you test, you modulate factor Z, and you see if it impacts factor A. And if it's working, then I feel like you can save quite some times of research, like classical research. You could save up to 5 or 10 years by not circling around what's known, but basically trying to go from test new hypotheses. And what we like is to try to test things that would be totally unpredictable from the literature. So it's predicted by the network or by machine learning programs, but you would never try that in more classical approaches. And I think this is the benefits potentially of machine learning. And so regarding training, I think this is where we think it's important to design I mean, what we've been calling gold standards. So whatever the links you're trying to do between your different omics, the idea is now you do some curated analysis of the literature, and you know, for example, these genes A control the expression of a protein B, and so on. And then, so you take your data sets, you basically use some a priori knowledge, which could be, we know, for example, those 500 genes are controlling the expression of those 2,000 proteins. Then you train your data set on that. You looked at your inferred network, for example, and you looked at how good you are in recalling your gold standard. So you can look at curves such as precision and recall, and basically you test your different models and how good you are to recover what's already known. And the idea is, and this is what we want to do, we want to try multiple different approach existing out there, and to try to estimate which one could be the best one to give us new hypotheses. The idea is to train it on what's already known. And if we find a method that recovers most of what's already known, we will feel somewhat confident maybe to implement the whole data sets and try to ask questions and get data extracted from that.
Yeah, okay. Are there more questions? For this project? Okay.
Yeah,
so,
okay.
Yes.
So if I understand well, you count more on deep learning just for opening some black horizons, a fishing expedition, more than machine learning. Yeah.
And for example, if you put back the last slide, like the slide 7, we've already tried that since 2012 and on the HIV field. And for example, once we got these big networks, we asked, and it predicted two new transcription factors, RAR-A and PRDM1, as being important for cell maturation and type 1 interferon production. And then we got back to the bench, we modulate their expression, and indeed, they were involved. And so now we have multiple examples, and this is, for example, helping us to go, as you said, to maybe to try to dig into new horizon of research that you would never go because it's not predicted by the existing literature, or the dots are not connected yet. But this is a parallel approach. Of course, we're still tackling this question using some more classical techniques that relies on existing literature. But we think, and we've already experienced the fact that there's some interest of getting into some semi or unsupervised approaches. And basically, we are interested by things that looks totally crazy. So you ask a question to the network, it replies an answer, and you look like, oh, come on, it's not possible. Based on the literature, I would never try that. And I think those are actually the hypotheses we are prioritizing in the lab. And when it's working, I think it's pretty cool.
Yeah, but then you accept the idea that it's going to be lots of wasting and garbage, because you will spend some time with the deep learning things that will not drive you anywhere.
It's true, but that's why, for example, for this first project, we spend a lot of time trying to, first of all, build a network that would be stable. So if you take the same data sets, you rerun it, you would get more than 90% of the edges would be the same. So we spend a lot of time to obtain a stable network. And then we spend a lot of time to learn how to use our network to make sure that we're only going to look at the top predictions. And so far, among the top predictions, I mean, we didn't get too many waste of time. But I think the key here was to make sure the network would be stable. So you take two data sets and you rerun it multiple times, and most of the time you're getting the same predictions, which was not the case when we started.
Okay, thank you.
Thank you very much. We now need to move on to the other presentation. Thank you, Michael.
So yeah, next one I'm calling Nicolas Lomeni.
I'm there. Thank you. Thank you, Themis, for the kickoff meeting. All these topics are very difficult to understand, so we just need to know each other a little bit more. As for us, it's a long story because we started to work on digital histopathology a few years ago. And the strategic project that we proposed to the Institute, it's the meeting of artificial intelligence and anatomopathology. So it's a big name for not radiology, but the next door, it's the pathology. So when people are doing biopsies. So you have an example of a biopsy there, but I will show you later on. The team is already running. Myself, Nicolas Lomeni, and Camille Kurtz, we are two associate professors. A PhD student, Chinre, she's there with us. Fula, that helped a lot to do the slides for today, because now she understands better what we want. And we already hired intern, Zuchan, with the help of the master project of the Institute. Is here also listening, and we are closely working with 2 or 3 physicians at the APHP, Jean-François Émile, PUPH, and Julien Calderaro, also PUPH, and also with Cécile Badoual, who is at our university. Next slide, please. This is a histopathological image, a wool slide image at very low magnification. And you can see that the small cat, nice cat there, it's a mainstream image that people use for macroscopic computer vision and machine learning topic. And it's just a small, very, very small part of the slide. So it's just to show you the big data in there. So we have to explore this kind of tissue image, which is digitized, and at various magnification. So this is the lowest magnification, but we can go to times 40. Next slide, please. Yeah, so it's a bit official there. So yes, we will. You have still already an overview what is digital pathology, but very short. What is an image in histopathology? Very big. And then we will explain how we stand now. Next slide, please. This field focuses on data management, right, and analysis based on information generated from digitized specimen slides. So for now, people, physicians, they are working with analogical microscope, but there is something new coming in the lab at the hospital, is the scanner from a manufacturer like Philips or Hamamatsu. And these glass slides are converted into wool slide images, very big image, like 10 gigabyte data for just an exam, like 100,000 pixels by 100,000 pixels of color data at various magnification. So there is first an issue about the management, handling of this data. And we chose a partner, the name is Cytomine, there is a typo, sorry, who is a Belgium company, like a spin-off of a Belgium university that helps for the online storage and annotation system, because annotation is a big deal for us. We need the help of the physicians to annotate the slides to do learning, of course. Then, of course, we need to analyze this image, these big images with computer vision and deep learning to ease the detection of histologic primitives, for the prediction of disease, for the classification of tissue. And last but not least, we need to integrate it in a clinical workflow pipeline. So that's the most difficult part in our field. So we have a lot of tools that get very high scores of classification, but then you need to put in real life. Next slide, please. So yeah, this is a nice paper if you want to dig into the details about where we stand in 2020 in terms of histopathological image analysis and deep learning approaches. So I will not go very really into details, of course, but we have the classical issues of computer vision, like segmentation, detection, and classification. And we go from the image to perhaps the genomic or the genetic subtype identification just based on the observation of the tissue. That's the goal, the final goal, I guess, for this kind of topic. So it's a little bit like the strategic project before. Next slide, please. So there are a lot of challenges, of course, because the image, the digitization process is not yet really standardized. Sorry, the image can be noisy, of course. There are biological variabilities because of the way the tissue is stained or cut. We are dealing with very large images, like 10 gigabytes, as I said, and image annotation, of course, is a tedious process. Next slide, please. So for now, we already have two projects going on. One, which is called POSHI, because it's the name of the phase 2 trial that will start this month with a big pharma and with Jean-François Emile. And we already had done for the last 3 years a lot of development and research, and we want to go to the next step, which is the development of a companion test to assist the physicians to segment the patients that will benefit from an immune drug, because it's very expensive and the counter effects can be very toxic also for the patient. So we need to choose exactly which patient will benefit from that, and we try to do it with this kind of tools. You can see annotation, image analysis, and quantification of the lymphocyte infiltration, for instance. So that's the big project we are on for the first months of this strategic project. And then we have another project with the Mondor Hospital, and it's done with Chinre, which is in this meeting, where we also try to develop deep learning models for the detection of tumor tissue out of wool slide images, but on another tissue, another database, other annotation. So of course you can see that there will be some bridges between these two projects, because we will use the deep learning models learned for the hepatocarcinoma cancer, for instance, and we will try to use it for the colon tissue with another staining, perhaps another magnification. So it's like a versatile transfer learning issues. And we are currently in the process of always acquiring and annotating new images with the three physicians who are working on the three different tissues or cancers. Next slide, please. So the next steps, yes, we need to improve the accuracy, of course, and the robustness of our models. We are starting this phase 2 clinical trial, and then we need to fine-tune to put some talent, as the guy from Microsoft said, in the models, and the talent is our PhD or our interns that will help to fine-tune and extend pre-trained deep learning models to various tissues, various magnification, various staining. And for me, it's really the final goal from a translational point of view is to assess the developed system within a real clinical workflow. And the last scientific one, GRAL project, is to be able to establish link between the visual appearance of the lesion, so the image, in the image, and the patient's genomic data that help to segment the patients in the immunotherapy process. Next slide, please. So Fula, who is helping us, will help for the data engineering, for the consolidation of the images that we have and their annotation, to improve the interface also for the image annotation. She will help, and she already had, for the understanding of the computational infrastructure that we can use with the Institut du Globe cluster of GPU and CPU that we try to use. And perhaps she will also help to participate to challenges that are coming, like the one from the Île-de-France, the challenge about AI and health. So we will try to do this kind of stuff with the help of the Institute. Next slide, please. And of course, she will also help for the development of the models, the deep learning architectures, and for the discovering of new computational biomarker in that kind of issue. And also she will help for the validation and the clinical workflow with the help of the two physicians that we are working on. Next slide, please. And I will end with this slide, because I have I think 5 more slides, but it's okay. It's just to give some flesh to the projects. So the diiP is in the center, the institute. Fula, who is the research assistant, will help us to supervise a little bit all these people, because it's like a startup. Zuchan, who is an intern that is funded by the institute, who just started last Monday, sorry. And you have the POSHI project, on the left, with Jean-François Émile, who is a praticien, professeur universitaire praticien hospitalier, PUPH, and Gulian, who is an intern from École Centrale, who help also for the certification, European certification, if we go for a companion test. And on the right, you have the team for the Mondor project, with Christophe Klein, who is a research engineer at the Cordelier platform of imagery, and Julien Caldarero, who is the PUPH with whom we are working. And so you have all the team, almost all the team there. And perhaps the next slide. No, we can stop there. Go to the slide before. No, before. Yeah, I will stop there. So thank you for your attention.
Thank you very much, Nicolas. Are there any questions for this project? Maybe something that you could explain to us a little bit more. So, what is the need for machine learning and deep learning in your case?
Okay.
So, is the goal to allow the doctors to do to analyze the results of the exams faster or better? So are the machine learning tools that we now have less accurate than the doctors or more accurate than the doctors?
No, they are less accurate, but you've seen that for now, but you've seen that the data, they are huge first. So they need help to explore that. I would say as a first pass, because sometimes you have a lot of exam that doesn't need to spend too many times. So it can be done, if it can be done by automatically, sorry, it will be good. But mostly, I think the next step will be to use machine learning to be able to predict immune class of patients without doing the genotype analysis, because it's expensive, but just by analyzing the image, the tissue. So I think the last step for the machine learning point of view is to be able to learn from tissues, image of tissues, and to do the connections with the immune class, because for immunotherapy, there are many different perspective for the patient, depending on the immune class. And that's we call the precision medicine. So the goal is the precision medicine, I will say, to be more adapted to each patient who is different.
I see. Thank you very much. Is there another question? One last question for Nicolas?
Yes, Themis, thank you. Isabelle speaking. Nicolas, thanks for your nice talk. You're very sensitive to the false detection rate. And how do you tune it? You set it high, you set it low. How do you handle that problem?
For the false detection, for now, we are not at this level of analysis of the results, because it's already a big deal to be able to handle these big images. So we are just trying to go to the precision of 80%, and we will be happy, 85%. So we are not still at the level at tuning very precisely for the false ratings. But of course, that will be the next part of the project. When everything will be set up, then we will go more in details with the results. So it's just starting. Thank you, Isabelle, for the question.
Okay, so thank you, Nicolas, very much for this presentation.
Okay, you're welcome. Thank you again for the kickoff meeting.
You're very welcome. So we will now pass to the third presentation. The third presentation comes from is led by Antoine Lucas from IPGP. Unfortunately, Antoine cannot be with us today, so I will just play back the presentation that he has sent us. And let me share my screen.
Good afternoon, everyone. This is a recorded presentation. Antoine Lucas speaking, PI of
of the Parker Research Project of the diiP call. As it stands, we seek for deciphering the topographic signature from various planetary bodies by merging expertise from Earth sciences, including remote sensing, geology, and geophysics, with state-of-the-art applied mathematics for image and signal processing. Topography, the surface configuration of a planet, bears the imprint of the processes that shape it. Deciphering the text encoded in the topography has been the goal for scholars for centuries, and those scholars looking into space, topography is a window in the processes that shape alien worlds. Here on Earth, it offers clues to how our planet might be different, and if so, why. Despite centuries of theory that the abundance of life is shaping the surface of our planet, the study of topography has yet to uncover a unique signal on Earth. Indeed, as recently as 2006, Dietrich and Perron, in their Nature's paper, who asked the question, "Is there a topographic signature of life?" concluded that none could be detected from terrestrial data available back then. Today, with the revolution in Earth observations from space, we can address this question with fresh eyes and extend it to the other bodies of the solar system. Doing so requires the interpretation and a wide range of datasets and cutting-edge mathematical approaches to their integrations. This integration and interpretation are the focus of this proposal. As it stands, evolution of landscape is controlled by erosions, and there is a consensus that there is a strong correlation between climates, such as rain precipitations, with erosion rates, such as incisions. As a matter of fact, we expect slow erosion in a dry landscape. As you all know, the erosion shapes the structure of the mountain belts, plays a key role in the feedback between tectonic and climate, and obviously, as for the Earth, modulates the ability of the planet. Slope dependent, such as diffusive transport, leads to convex hill slope, and when the topography is literally perturbed, the transport direction causes the high points to lower and low points downhill to fill in. This results in a smooth topography. In contrast, transport that depends on water flow and slope advex sediment and produces concave uphill slopes. Flow concentrations resulting from lateral topographic perturbation lead to incision. And so the competition of these two processes leads to a diffusion-dominated ridges and an advection-dominated valleys. As we know, the emergence of life on Earth has fundamentally altered the evolution of the planet. Nonetheless, there is no evidence that there is a unique topographic signature of life on Earth, unique being that a landform would only exist in the presence of life. Similar convex landscapes are actually observed on Mars, as a matter of fact. So we may expect that the topographic signature of life might be subtle, in the sense that we may diagnose it in the frequency of occurrence and of scales of landform properties. To exemplify this statement, one can look at the topographic slope versus the drainage area for various landscapes. As shown here, biotically influenced landscape clearly differs from abiotic landscape. So as for planetary exploration teaches, an abiotic planet looks different from ours but exhibits familiar landforms. Therefore, subtly we aim at detecting would require global high-resolution topographic data over a few planetary bodies. Those were just not existing back to 2006. In the past 15 years, global high-resolution topography data have become available for Mars and for the Moon, and to some extent to other bodies such as Titan. However, early attempts to map the Earth's topography has been limited by spatial resolution and, more importantly, abundant vegetation that hinders the land surfaces. As you know, back to the Space Shuttle era, the 30-year missions have been able to provide global surface model. Due to the radar design, these datasets are not representative of the terrain relief, but account for any object above the surface, including vegetation. This changed in December 2018 with the arrival of the Global Ecosystem Dynamics Investigation, called JEDI, which is a full waveform LiDAR installed on board the International Space Station. Over the minimum of 2 years mission, and now we know that this has been extended, JEDI will provide an estimate of a global, at the global scale, of about 10 billion waveform LiDAR observations between 51 degrees north and 51 degrees south of latitude, and produce observations of both ground and vegetation height, notably thanks to the fact that JEDI is the first instrument to provide complete waveforms of the LiDAR echoes at the global scale for the Earth. Thus, for the first time, we can literally see through the living skin of the Earth and compare Earth's topography to that of neighboring planets and moons, the topography of which is not influenced by vegetation. Therefore, the Parker's project goals are evaluating the occurrence frequency of abiotic versus biotic landscapes, deciphering advecting control versus diffusive control landscape, and as a secondary output, elucidating the controls on river carbon's fluxes to the oceans. Indeed, one can ask if the hypothetical frequency distribution of natural landform patterns is being controlled differently on an abiotic versus a biotic planet, and if, in particular, patterns typify a biotic planet. The Parker project aims at evaluating this hypothesis throughout the analysis of planetary LiDAR data coupled with finer elevation data generated from photogrammetry by taking benefit from the big data and machine learning approaches. This is why fusion algorithms that lead to super resolution products needs to be applied to this data. We will analyze existing publicly available remotely sensed data from space LiDARs, namely JEDI, MOLA, and LOLA for respectively the Earth, Mars, and the Moon. In addition, we will take two complementary approaches to answer how abiotic versus biotic and anthropogenic factors drive the flux of dissolved inorganic carbon, called diiC, and the dissolved inorganic carbon, diOC, to the ocean. We will leverage recent advances in machine learning to generate predictive models of river fluxes from existing watershed characteristics derived from the JEDI land surface elevation and topography, as well as JEDI above-ground biomass density data, Landsat-derived land cover maps, bedrock and superficial geologic maps, and local and global climatic datasets, such as WorldClim for continent-scale catchment and more local measurements from small watersheds. This approach has a global coverage consistent with the requirement of large-scale approaches described in the call. In addition, we will leverage 50 catchments distributed worldwide for which there are additionally detailed geochemical constraints on carbon dynamics, for example, isotopic measurements of river chemistry. In regard to the main objective of this project, we identify three main steps. Step 1, which corresponds to a planetary LiDAR fusion and super resolution accounting for optimization and adaptation towards big data issues. Step 2 being generation of the high-level products that will lead to a subsequent analysis. And then step 3, machine learning ingestion to the high-level products from step 2 to extract features at various scale in order to 1. Detect if life is responsible for specific patterns by comparing terrestrial data with others, and also to distinguish various kind of erosions that decipher the topographic of those planetary bodies. And in 2, use machine learning to integrate new space-based measurements of forest height and topography with other remotely sensed data and uncover the controls on river carbon fluxes at the global scale. So in order to exemplify what can be done in terms of 3D extractions, here you can see a tree that can be considered as being a 3D structure, but actually this whole depending on the scale that you are looking at. So you can decipher various sub-blocks being 2D, 1D axis or 3D structure, and this is even more complex when you look even closer and again. So these have been proposed from being ingested into machine learning algorithms by Brodie and Lag in 2012. When you look at the covariance distribution of 3D coordinates obtained from LiDAR data, and here it's an example from the Mont Saint-Michel Bay, when you see dunes, vegetated dunes on the grayish area of these 3D clouds. And when you look at various scales, you can see that the biotic, being the vegetation, and the abiotic, being the dunes, don't show the same distributions. And we can considering this as an input for machine learning 3D extractions and be applied at the global scale. So to tackle the issues that we want to address with this project, we want to create a synergistic collaboration between two laboratories of Université de Paris, Institut Physique du Globe from Earth Sciences and Map 5, Mathématiques appliquées de Paris 5, from the mathematical point of view. So IPGP has various expertise in remote sensing, in extraction of forest characteristics from LiDAR. He also possesses a world-class expertise in study of river chemistry, transport, weathering, and erosion processes. The Map 5 on itself has a strong expertise in mathematical models related to image and signal processes, covering various applications such as image restoration, inverse problem, tracking, registration, and so on. And therefore, we aim at merging our own expertise from our respective disciplines towards some efforts with GPU implementation and optimization that needs to be carried out as we will face the big data issues. So we will take advantage of the required Chen Liang, which is an expert in GPUs with big data view as well as machine learning of time series, and he will strongly contribute to the project. So to finish, I would like, on the behalf of the whole team, deeply thank the diiP committee for supporting our research, and I thank you for your attention.
Okay, so that was the presentation. I'm not sure if someone from this team is present, but maybe we cannot ask questions. Just to conclude this session, I would like to say that I'm definitely very excited with all the projects that are currently running. I'm sad that we could not support all the project proposals that arrived to us. But in any case, I urge all of you, people that are supported and people that are not supported this year, to get engaged in the community that we have in diiP, to try to learn new tools, techniques, ideas that could be useful for your work, and also to network. So one of our goals is to provide a platform, an opportunity for you to talk to other people that have similar problems, that may have a technique that can actually be helpful for you. Okay, so having said that, we can now move on to the last part of our agenda for today, and this is the second invited talk for today by Dr. Ian Foster. Ian Foster is the director of Data Science and Learning Division at Argonne National Lab in the United States. This is one of the largest scientific labs in the States, and one with a very long history. And Ian, the floor is yours. I'm very glad that you were able to be part of this event.
Okay, bonjour tout le monde. I'm sorry I could not be there for the earlier talks, but I'm currently in New Zealand, escaping various things in the States. And so it's a little bit early here, but anyway, it's nice to see you, at least some of you, virtually. I'm just going to work out how to share my screen, and then we can get started. Here we are. Okay, so 1 second. No, not that. No, got it, I think. Okay. Good morning, everyone. So, or good afternoon. Apologies. Yeah. So I'm Ian Foster. I'm, as said, director of this division at Argonne. I'm also a senior scientist there and a faculty member at the Department of Computer Science at the University of Chicago. This is a picture of Argonne up here in the upper right, behind this odd-looking robot. And what you'll see at the moment, you just see a lot of snow, but at the moment you see in the bottom left, for example, the advanced photon source, a bit like the European synchrotron source in Grenoble. It's one of a number of research facilities there, as well as a lot of scientists, including a lot of computer scientists and applied mathematicians, in fact, many of whom, in fact, have connections with people in France. There seems to be a strong connection between Argonne and French institutions. In any case, so I'm going to talk to you today briefly about this, what I call here, translational research and data-driven discovery. And I should admit, to start with, I'm not a data scientist per se, although I have many friends and colleagues who are, but I've been involved in data-driven discovery in various ways for some years. But first of all, a few words about what I mean by translational research, because I think it's an interesting concept. So I think we all know that computing has this wonderful property that unlike other sciences, which are concerned with properties of the natural world, computing also has this engineering dimension where you can create astonishing things very easily, as something that Frederick Brooks pointed out many years ago, which of course then leads to the question of what should one create. I've always found it interesting to work to create things that are going to be used by real people, by perhaps large groups of real people, and also by scientists, because scientists I find often have particularly interesting problems to work on, and when they use your tools to build something interesting, then it's usually something that you feel good about having enabled. So this notion of building tools that are meant to be used is, well, you might say, why would I build any tool if it wasn't going to be used? And of course, there's some truth in that. But this this notion of translational research seeks to formalize this concept. Translational medicine is quite a well-known idea by now. The idea is, as I quote here from this article by Abramson and Parashar, in applied research, they say, well, you seek to build something that may have a real-world application, and I think that's true of a lot of computer science. In translational research, findings are applied as a specific phase of the research plan, and the success or not of that application is an important evaluation and feedback mechanism for the research that you're doing. So that's a mode of work that I've been pursuing for some years. So let me talk about sort of three sets of activities that I've undertaken in that context, which have this sort of translational approach to data-driven discovery. So the first one goes back some time, perhaps a couple of decades, when a number of large scientific projects were facing substantial scale barriers to what was essentially data-driven discovery. The LIGO detector in the US and Virgo detector in Europe, the Large Hadron Collider in Switzerland, and the climate model intercomparison project being performed by the Intergovernmental Panel on Climate Change all face the need to, in various ways, collect, distribute, analyze large amounts of data. And I'll give you some data volumes in a minute. In the context of large international, mostly LIGO, arguably only national collaborations. So I got involved in these projects early on, and with colleagues, formulated this notion of what we came to call grid computing, mechanisms that would allow us to pool, aggregate, and apply in a collaborative fashion large quantities of distributed computing software, data, and other resources. And these mechanisms were then applied in varying ways. This is a slide actually from 2012, but so it gives some scale quantities of that time. They've now increased by probably more than one order of magnitude, but LIGO processed a petabyte of data. This was, I think, before they just discovered, detected gravitational waves, but it was not too long before. The Large Hadron Collider, showing here some stats just from the US component of the worldwide LHC computing grid, processed many petabytes of data in order to detect and measure the mass of the Higgs boson. And then the Earth System Grid collaboration, the Earth System Grid Federation collaboration, pooled climate simulation data from many centers worldwide in order to obtain strong signals of climate change by comparing the results obtained with different models. So all of these to varying degrees built on this Globus Toolkit software that we built, which was fun. Each of them also led to a Nobel Prize, although for ESGF it was only, or IPCC I should say, it was only a peace prize, not a science prize, but nevertheless we can claim some impact in that regard. In each of these cases, this is very much each was very much a translational research project. There was a goal not only of solving underlying computer science problems, but also in building robust production solutions in partnership with scientists who, often ended up doing a large amount of the work, but nevertheless, in a way that depended closely on the work of the computer scientists. I'll skip that. So yeah, myself and my colleague Carl Kosman recently just wrote an article where we tried to reinterpret the work that was done in this space, sort of mostly in the 2000s, in light of this concept of translational research. And I found the analysis, the process of conducting that analysis and some of the results interesting. And perhaps there are things to be learned here in the context of your new institute as you think about how to apply data science techniques to problems, I assume particularly in the sciences. So that's one first thing I'll mention briefly. The goal there was to deal with scale barriers in science. We also observe increasingly that small science, if you like, the science that's conducted often, perhaps not so much nowadays, but still I think to an extent with data on disk drives, on desks and racks of servers. The problems that they face are often problems of complexity around data lifecycle management, as I sort of summarize in this this slide. In the sort of project starting in the year 2000 and going forward, 2010 and going forward, we sought to understand how one might be able to leverage concepts of cloud computing to automate some various elements of the research data lifecycle by enabling people to outsource their problems to cloud services. And actually we found that to be quite successful. We built a service called Globus, which was extensively used in the US and used quite a bit in other countries like New Zealand, Canada, the UK, and not quite so much in continental Europe, but providing a set of services, sort of the way that cloud services automate so much of our ordinary lives today, they seek to automate things that dominate in at least some people's research lives, things like moving data, sharing data, automating science workflows. I won't go into more detail on that, but just point you at globus.org if you'd like to learn more. But it's been fascinating to watch how taking these concepts of well, outsourcing to cloud can make a difference in science as well as in e-commerce. And we recently had a milestone where we had moved a total of exabyte of data, which would have been a lot a while ago, but nowadays, of course, it's not as much data as it used to be. So I'll just give you one example of the sorts of things that people are doing with the Globus using the advanced Photon source, which I showed you briefly in the title slide. There was a lot of work, of course, at the APS, as at other synchrotron facilities, on crystallography of SARS-CoV-2 proteins. Argonne was focusing particularly on room temperature measurements. And we used these Globus outsourcing services to automate these end-to-end data pipelines. So of course, doing this has got nothing to do with data science, except that by reducing friction, it allows scientists who would not otherwise be able to apply data science methods to do so in ways that they couldn't otherwise. So my final few slides will just say a bit about what we're focusing our attention on at the moment, where I think there's probably a lot of overlap with work going on at in your institute. So this is a quote from the US Department of Energy, which funds Argonne. It's an interesting quote because it's in the budget justification for the agency, for the department. And that, it notes basically that data-driven methods, by which they mean primarily machine learning, AI methods, being applied at extreme scale, tightly coupled to experiments and user facilities, are going to be central to the next set of discoveries in various areas of science, etc. So if you believe that, which they do, and I think we do to a significant extent, then we live in exciting times for those who are working in AI plus science. So we at Argonne and also at the University of Chicago increasingly are very deeply invested in this notion. And I'd say it's sort of for two reasons. We've got exciting new capabilities being developed on the left. We know about those, of course, from many sources, but also scientific problems that pose increasingly challenging requirements, which seem hard to address with existing capabilities. So very large data volumes, the lack of or the termination of the continued exponential growth in computational capacity, which prevents us from applying, for example, pure simulation-based approaches to understand certain things, and then the increasing complexity of problems which are beyond perhaps people's ability to model. So anyway, so what is going on at Argonne in this space, where we're certainly applying this translational approach to scientific problems in, I would say, mostly so far fairly straightforward manners, which is, I think, the case of most AI for science projects. Trying to make sense of large data sets, building predictive models that perhaps are better than those that can be created by humans alone, etc. And I've just got 6 examples shown here of many, probably more than 100 that are underway at the lab. Again, I won't go into detail, but just to give you a sense of some of the breadth of activity that's going on. So for the most part, these are projects where we might be doing things like learning predictive models from data. So a lot of activity in materials and chemistry, for example, an area of particular interest at Argonne, but also in other spaces. Or in the context of our scientific instrumentation, solving inverse problems in a model-free or model plus data driven manner, or generating large collections of synthetic data. So these are all actually seem to be quite impactful and successful approaches, but they're not certainly where we want to be in the next over the next decade or so. So we have identified a set of areas where we see bigger opportunities. So I just we try to group them into 6 here. Maybe I'll say a few words about each. To the extent that we can build models or train machine learning models, often deep neural network models, on the basis of large amounts of data, we can start to use those learned models to replace data in various places where we use data in scientific investigations. So a lot of, for example, materials properties, rather than having large databases, we may just access a model to get a good approximation, hopefully one with bounded accuracy, that we can use in, for example, a problem like screening large numbers of molecules for as potential, COVID therapeutics. So we know how to build models, for various properties at the moment. There's still a lot of work to be done to build models that have interesting properties, for example, so that they can be used in an understandable manner, so they can be combined with each other, so they can be used without revealing information that was used to train the model in the first place. So that's one rich set of research for us. A second area of interest, and this is perhaps, I guess these are all fairly vague, but hopefully I'll be able to shine a bit of light on what I'm meaning, is rethinking experimental discovery processes. So at the moment, experiments in a very simplistic manner proceed sort of as follows. A scientist thinks hard about a problem, has some insights, proposes an experiment to test that insight. To a large extent, we'd like to get to the point where models can be used for experiments, and experiments are used primarily to improve models. So you query a model to find out what properties a particular material might have, or what might happen under a particular climate change scenario. If uncertainty seems to be high or results are surprising, then you might conduct experiments that would then provide feedback to the model development. So it's a very different way of undertaking scientific investigations. In pursuit of this notion of using experiments to improve models, then we'd also like to be able to pursue various questions, or semi-autonomously, perhaps some cases fully autonomously. And this may involve, for example, in material science, building high throughput automated labs of various sorts. So I think I'll stop. I won't say more about the other three, but you get the idea of some of the areas in which we want to work. So we're starting, as at least my group is starting to build tools that can help reduce friction in pursuing some of these approaches, like the DL Hub, Data and Learning Hub for Science, to capture and enable on-demand access to learnt models. We're investigating mechanisms for automatically creating and synthesizing surrogate models for expensive components of simulations. The goal here is to speed up. It could be a materials science model, a climate model, a weather model, or something else, by learning quick approximations to functions that are called repeatedly. And it seems that one can do that with a fair degree of accuracy and perhaps increasingly also confidence in results. Big picture, I think, going forward, we have this opportunity to build a new sort of set of tools for data-driven discovery. These would be applications that might perhaps be created by the community that could be used to, for example, design things, run experiments, to discover things, and to understand things. And one might imagine that a system for AI-enabled design could be used to design materials, polymers, organisms, ecosystems. An AI-enabled experimental system could be used to drive a wide variety of different self-driving labs. And if we can really get a handle on how to do AI-enabled scientific comprehension, then we will be able to integrate not just data sets, but literature, science, news, I guess, tips about who was doing what, with a goal to providing expert advice to scientists about what is known, what is uncertain, perhaps what is worthy of investigation. If we could do that, that would change the way that people do science in some really interesting ways. So let's see, move on. Oh yeah, so, and then based on this, so there's might be some other such components, but I think an interesting challenge for those who want to engage in translational research and data-driven discovery is to think, well, what are these systems? Assuming that they are going to be built, then whoever builds them will outcompete those who don't build them. So how do we build the collaborative communities that will build them and make sure that they are built in a way that does what we want them to do? Okay, so then one last slide. This is where we hope to get to in sort of this AI, translational research in AI for science, faster discovery, increasingly autonomous laboratories, applications that can allow us to simulate systems that are larger, more complex, more in a way that's either more accurate or faster, or more reliable, or something maybe along multiple of those dimensions. And then transform how we use, how we access literature and data. And then maybe under the covers as well, there'll be a lot of work. There's a lot of work to be done to change how we actually operate scientific laboratories, which are still done in a rather manual manner, I would say, at the moment, old-fashioned manner at least. So thanks for listening. I think I used up my time, but I hope at least a little bit of that was of interest.
That was definitely interesting. Thank you very much, Ian. So actually at the beginning, I forgot to mention that Ian is joining from New Zealand, where now it's 6:30 in the morning. So we really appreciate this.
Pleasure. I put a Chicago background on just to make it you see what it's. I think there's I need about 10 centimeters of snow has fallen already today, I think. Yeah.
It's also snowing in Europe now. So these are some extreme phenomena happening this year. Are there any questions for Ian? And maybe in the meantime, I can ask one question. So Ian, one of the things that you mentioned as an interesting direction for AI, AI and data-driven discovery, are the inverse problems. So, for example, going from a spectra back to the structure.
Mm-hmm.
So, could you tell us some more about this? So, is this something that is actually going on now? Do you have interesting applications? Why do we need this? How exciting is this?
Yeah, no, I think it's very exciting, and I'll say a few words about it. I'm not a mathematician, but at the advanced photon source we have for example, which is one of which is a single facility, but with 60 beamlines running very different data collection methods, and they're all, of course, shining lots of photons at some subject, either it's fixed or evolving in time, collecting large amounts of data, and then wanting to understand something about the underlying structure. And in many cases, the sort of forward models you may have models that you may have methods that you can use to reconstruct the structure, but they are very expensive. So one reason for using machine learning is to obtain very inexpensive or fast, perhaps more approximate reconstructions. And you may be using this for example, because you want to be able to steer the experiment while it's happening. In other cases, I think there's a lack of good methods for performing the reconstruction or solving the inverse problem in any other way.
I see. Yeah. Is there any other questions for Ian?
Well, thank you all.
And sorry, there is one question.
Yes.
So from Christophe. So is this new landscape of experimental science, in this new landscape of experimental science, what is the roadmap for test beds? So what is the role that test beds can play?
So perhaps you mean environments in which we can experiment with different sorts of approaches. I think that's a very interesting question. So most the automation of experiments is primarily done at the moment by the acquisition of expensive apparatus from companies that have designed them to perform some particular set of operations reliably and rapidly. And perhaps AI-driven discovery needs a somewhat different approach. You want to be able to quickly reconfigure apparatus to perform different measurements or to synthesize different materials. And so there is a growing community of people who are interested in this question of how we can define what you might call software-defined laboratories, in which there'll be much more ability for computer scientists to configure systems. And for that, I think we need test beds, but what they should look like, I think we're just trying to work out. In fact, we have after this. A little bit later today, I'll be having there's a workshop at Argonne to consider that question.
Okay. So thank you very much once again. It was not an honor for us to join our kickoff event.
And yeah, very good. Well, good luck for your institute, and hopefully I can visit in person one day.
Definitely, yes.
Welcome.
Thank you very much.
Thank you very much.
Thank you. Bye-bye.
Bye, Ian. So to conclude today's event, I would like to ask Eric, he's the vice director of diiP, to offer some thoughts and conclude today's event.
Thank you, Themis. Can you hear me well?
Yes.
Yes, very good. Thanks. Well, it's getting late. I don't want to be long now. I think we had a great kickoff meeting today. First of all, I'd like to thank all the speakers. I think we had a lot of insightful talks today. I guess that with me, you should be struck by the large diversity of the topics that we've been hearing from. A large diversity of application, computer science, of course, but physics, geophysics, astrophysics, medical science in various forms, biology, chemistry, and linguistics, and so on and so forth. So I think this is a main message and a main feature that I get from the meeting today. This large diversity, and this led me to argue that diiP will not only be this forum where the exchange of data science and know-how about data science will be done, and where we learn how to better handle the data we are facing, or learn from new algorithms and so on. But also, it will be a real university institute in the very sense of university, touching with questions that other fields are facing, look at other perspectives, and look at things from other perspectives. So I think this is going to be very exciting, and I think I very much looking forward to the future of this institute. Of course, I think what we are missing now is really meeting in person, but hopefully this will come from in a not so far future. So well, I'd like to wish long live to the diiP, and wish to see you sometime in a diiP meeting very soon. So thank you for joining today, and well, see you next time at the diiP meeting then.
Thank you very much. I'm sure that we will soon have some other meeting, hopefully in person, and that would also be an opportunity to hear about the results of all these projects, which I'm really looking forward to. So thank you very much to everyone. Thank you very much to Anais as well for organizing all this.
Of course, my pleasure. And thank you everyone for being here this afternoon. It was great.
Thank you. Have a nice evening.
Okay, bye-bye. Have a nice evening.
Bye.